In our fatty acids podcast, we're going to talk about the two classifications of lipids, both saponifiable versus non-saponifiable lipids. And we're also going to talk about the structure of fatty acids, and we're going to talk about what saturation versus unsaturation does to the physical properties of those fatty acids. So lipids can be classified into two groups, either saponifiable or non-saponifiable. If they are saponifiable, a newer word that we like to use instead of saponifiable is hydrolyzable. So essentially, these lipids can act as esters. We can break the ester bond apart with water. These include your triglycerides, which will be the next podcast you watch, fats and oils, it'll be waxes, and phospholipids. So we're going to go through each of these different types of lipids in future podcasts. And I just wanted to show you real quick right here. This is an example of a wax that has a long carboxylic acid and a long alcohol chain that came together to form an ester. If this is saponifiable or hydrolyzable, I can break this ester linkage and I can reform an alcohol and a carboxylic acid. So we have classes that act as esters and we have others that don't. Non-saponifiable lipids are ones that don't act as esters. They cannot be hydrolyzed. These include our steroids, prostaglandins, and terpenes. We're going to focus on steroids more in this class for our non-saponifiable lipids. All right, so let's talk about the properties of fatty acids, and then we'll go into some more details about the structure of them. But again, both of those are very interrelated. Fatty acids are carboxylic acids on one end connected to very long hydrocarbon chains. They can be 12 to 20 carbons. So this is not your typical carboxylic acid because it has such a long hydrocarbon chain. Usually these are straight chains. You're not going to see any branches coming off of these. And they usually have an even number of carbons. So typically in nature we see an even number of carbons on fatty acids, which is kind of an interesting trait. They can be saturated, meaning in that hydrocarbon chain you only have single bonds, or they can be unsaturated, meaning they have at least one double bond, maybe more. In nature, we see that the double bond in fatty acids are typically cis double bonds. However, we're going to find out later that you can induce a trans double bond, and we see this done with fatty acids that are used in food. When we talk about fatty acids, we can describe them as being either mono unsaturated or poly unsaturated. If it's mono unsaturated, remember that mono is one, it has one double bond. If there is more than one double bond, we stop counting and just call it poly unsaturated, so two or more double bonds. Your carboxylic acid portion, that carboxylic acid head is considered polar. Because it is polar, the head of your fatty acid is going to be hydrophilic or water-loving. The long hydrocarbon chain or tail is just made of hydrogens and carbons, which have nonpolar bonds, and therefore they're hydrophobic. So we see two different sections in your fatty acids, a very short and small polar head and a very long nonpolar hydrophobic tail. Because of this very long 12 to 20 carbon hydrocarbon tail, fatty acids are going to be insoluble in water. All right, so you guys are going to be looking at a lot of different fatty acids on your homework as well as your guided practice. The good news is you don't have to memorize the names of these fatty acids along with their structures, but you are going to have to answer a lot of questions regarding the properties of fatty acids and what the polar portions of the fatty acid is versus the non-polar. So on the next couple of slides, we're going to practice that. All right, I wanted to show you the structure of the fatty acids. Specifically, this is palmitic acid, which is palm oil. We're going to look at it in condensed structural formula, skeletal, and then ball and stick so that you can see the different portions of it. So palmitic acid has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 carbons in its chain. So it's definitely classified, it's between that 12 and 20, it's classified as a fatty acid, and it's going to have a carboxylate head. Skeletal structure, you're going to find out why skeletal structure is so amazing when it comes to drawing your fatty acids, because it's going to save you a ton of time. Remembering that where two lines come together is a carbon and that the hydrogens are not shown, but they're assumed to complete the octets for those carbons. All right, let's look at the ball and stick model because they're showing us the different portions. So here we have a polar head. You have polar carbonyl with dipoles, and you have a polar OH group. Because of this polarity, because you have a difference in electronegativity, you are going to have a hydrophilic region. This is your polar, and we call them a head on fatty acids. It's hydrophilic, it's water-loving, it's going to interact with water. Your long chain of carbons and hydrogens has all nonpolar bonds, and therefore this is your nonpolar region. We consider this hydrophobic. It's not going to be soluble in water. Because this chain is so long and because the polar head is situated at one end versus in the middle or anywhere else, we cannot overcome the nonpolar region with the polar head. So it's going to be insoluble in water. So if you were to add this fatty acid to water, you would see it separate in layers in an insoluble layer, just like adding vegetable oil to water. We are once again going to talk about the difference between saturated versus unsaturated fatty acids because, again, it's important to us. So stearic acid comes from cows or steers. Stearic acid has a long chain that is considered saturated with hydrogens. So this is a saturated fat. Because it's saturated, notice that if you were to have multiple stearic acids together, they're going to sit flat together. They're going to be able to pack tightly together. Saturated fats, if you remember from last unit, are going to be solid at room temperature. It's going to take a certain amount of heat in order to separate those molecules. So they can be melted, but the melting point is going to be a lot higher. As we mentioned in a previous slide, when you do have a double bond, that double bond is usually going to be a cis double bond rather than a trans. At least that's what we find in nature. And notice that the cis double bond sends those two arms of your fatty acid into that triangle position. So they have this kink in them, and because of that kink, they're not going to be able to pack tightly together. So at room temperature, we expect our unsaturated fats to be liquid. So you can think of all of your vegetable oils, safflower oil, olive oil, all of those are considered unsaturated to some degree. They may have more than one double bond, but they're going to have cis double bonds. Therefore, they're going to be liquid at room temperature. So it doesn't take as much heat to get them into the liquid state. I feel like we've talked about this before, but we're going to bring it up once again. We're going to talk about what your level of unsaturation does to the melting points of your fats and oils. So here we are seeing these top ones are they are saturated fatty acids, so they have all single bonds, no double bonds. Look at the melting points on these, and these are in degrees Celsius, so they have fairly high melting points. It's going to take putting these guys on the stove and getting them pretty hot before they're going to go from a solid at room temperature to a liquid. The second that we start adding double bonds, and here this is showing us our number of double bonds, palmitoleic acid has 1, oleic acid has 1, and then we see 2 and 3 double bonds. As you start to increase the level of unsaturation, we see that the melting point gets lower and lower and lower. So these are incredibly low melting points, which means just at room temperature, they're going to be liquid. So as we increase unsaturation, or as we increase the number of double bonds, the melting point goes down.